Have you ever wondered why light can't escape from a black hole? Let's dive into the enigma of black holes and shed some light on this fascinating celestial phenomenon. Imagine a region in space where the gravitational pull is so intense that nothing, absolutely nothing, can escape its clutches. That, in essence, is a black hole. These cosmic behemoths are not visible to the naked eye, but their effects on nearby stars and gases reveal their presence. But what makes a black hole a black hole? There are three basic properties that define them: mass, size, and the event horizon. Let's break these down. Firstly, the mass. A black hole is formed when a star, at least 3 times the mass of our Sun, collapses under the weight of its own gravity. This collapse results in a dense core known as a singularity, where the mass is packed into an incredibly small space. Next, the size. You might think that something with such immense mass would be gigantic. Surprisingly, this isn't the case. Because the mass is so densely packed, a black hole is actually quite small. To give you an idea, a black hole with the mass of Earth would be about the size of a marble. Finally, the event horizon. This is the point of no return. Any matter or light that crosses this boundary is forever trapped within the black hole. The event horizon is essentially the edge of the black hole, the boundary that separates the known universe from the unknown depths of the black hole. These properties combine to make black holes among the most intriguing and mysterious objects in our universe. Their intense gravitational pull and the fact that light cannot escape their grasp have puzzled scientists for decades. So, black holes are powerful and mysterious, but why can't light escape from them? To understand this, we need to delve deeper into the realms of gravitational pull, the nature of light, and the very fabric of space-time itself. To understand why light can't escape from a black hole, we first need to understand the concept of gravitational pull. Gravity, in its simplest form, is a force of attraction. It's like an invisible thread that pulls two objects towards each other. It's the reason an apple falls from a tree straight down to the ground instead of floating away into the sky. But gravity isn't a one-size-fits-all kind of force. It's stronger or weaker depending on two main factors: the mass of the objects and the distance between them. The larger the mass of an object, the stronger its gravitational pull. That's why you feel a lot heavier standing on Earth than you would on the Moon, which is much smaller and has less mass. Now let's think about black holes. A black hole is an area of space where gravity is so strong that nothing, not even light, can escape from it. This is because black holes have an incredibly large mass, all crammed into an incredibly small space. This extreme concentration of mass creates a gravitational pull that is off the charts. You might be thinking, but light doesn't have mass, so how can gravity affect it? Well, according to Einstein's theory of general relativity, gravity isn't just a force that pulls objects with mass. It's a warping or curving of space and time around a massive object. So when light comes near a black hole, the space it's moving through is so curved, so warped, that the light can't move in a straight line anymore. It gets pulled into the black hole, never to escape. So gravity isn't just about apples falling from trees, it's about the very fabric of space and time being manipulated by mass. It's this powerful and complex force that makes black holes the fascinating and mysterious phenomena they are. Now that we understand gravity, we can start to see why light can't escape a black hole. The key to understanding why light can't escape from a black hole lies in the event horizon. The event horizon is a theoretical boundary that encircles a black hole. It's the point of no return, where the gravitational pull becomes so immense that escape is impossible. Now let's delve a little deeper into what exactly this means. The event horizon is essentially the edge of the abyss, the last outpost where light and matter can, in theory, still escape the black hole's insatiable hunger. But beyond this boundary, the rules change drastically. The gravitational pull becomes so extreme that nothing, absolutely nothing, can escape its clutches. But what about light, the fastest thing known to us? Well, the speed of light is a universal constant, approximately 186,282 miles per second. This speed is so fast that it could circle the Earth over 7 times in a single second. Yet, it still isn't enough to escape the gravitational pull of a black hole's event horizon. Here's why. To escape the gravitational pull at the event horizon, an object would need to travel faster than the speed of light. However, according to Einstein's theory of relativity, nothing can exceed the speed of light. This isn't just a rule, it's a fundamental law of physics. As light approaches the event horizon, it gets sucked in, just like everything else. The gravitational pull of the black hole bends the path of the light, causing it to spiral inward. This means that the light never gets the chance to move away from the black hole and continue its journey across the universe. So, the event horizon acts like a cosmic trapdoor. Once you cross it, there's no coming back. It's like stepping off the edge of a cliff in the dark, where the ground suddenly isn't there anymore. In conclusion, the event horizon is a point of no return. It's a boundary where the gravitational pull is so strong that not even light, the fastest thing in the universe, can escape. Even light, the fastest thing in the universe, can't escape the event horizon of a black hole. The final piece of the puzzle involves Einstein's theory of relativity. This theory, a cornerstone of modern physics, revolutionized our understanding of space, time, and gravity. To put it in simple terms, Einstein's theory of relativity describes how the laws of physics operate in a way that is the same for all non-accelerating observers. It also tells us that the speed of light within a vacuum is the same, no matter the speed at which the observer is moving. This theory is split into two parts: special relativity and general relativity. Special relativity, proposed by Einstein in 1905, introduced a new framework for all of physics and proposed new concepts of space and time. It tells us that space and time are intertwined into a single continuum known as space-time. Events that occur at the same time for one observer could occur at different times for another. As we move to general relativity, Einstein took this a step further. In 1915, he determined that massive objects cause a distortion in space-time, which is felt as gravity. The more massive the object, the greater the distortion. Now let's bring black holes into the picture. A black hole is an extremely massive object, so its gravitational pull is incredibly strong. So strong that it distorts space and time around it. This distortion creates a sort of well in the fabric of space-time, a well so deep that nothing, not even light, can climb out. This is the reason why light cannot escape a black hole. It's not that the light isn't fast enough. No, it's that the space-time around a black hole is so distorted, so warped by the intense gravity, that all paths the light could take lead back into the black hole. So the gravity of a black hole distorts space and time to such an extent that light cannot escape. The light, once it crosses the event horizon, is destined to remain within the black hole, forever trapped in its gravitational well. Let's recap what we've learned about why light can't escape from a black hole. We initiated our journey by delving into the enigma of black holes. These astronomical phenomena, cloaked in mystery, are regions of space-time exhibiting gravitational acceleration so strong that nothing, not even particles or electromagnetic radiation such as light, can escape from them. The idea is mind-boggling, isn't it? We then moved on to discuss gravitational pull, a fundamental aspect of black holes. Black holes possess an intense gravitational pull, significantly stronger than anything else in the universe. This extreme gravity is what gives black holes their name. They're so powerful that light can't escape, rendering them black to our observations. The event horizon came next in our exploration. This is the point of no return around a black hole, where the gravitational pull becomes so strong that escape is impossible, even for light. It's the final frontier for light, if you will. Beyond this point, light is forever trapped, unable to break free from the black hole's grasp. Lastly, we touched on the theory of relativity. Einstein's theory of relativity fundamentally changed our understanding of the universe. It revealed that space and time are interwoven into a single continuum known as space-time. And it's this space-time that is warped and curved by the mass of a black hole, making it virtually impossible for light to escape, because you see, in the vicinity of a black hole, space-time becomes so curved that all paths, including those of light, lead back into the black hole. In essence, the answer to why light can't escape from a black hole lies in the interplay of these factors: the intense gravitational pull, the point of no return, that is the event horizon, and the warping of space-time as explained by Einstein's theory of relativity. And there you have it, the fascinating reason why not even light can escape the powerful grasp of a black hole.